we were talking about group actions and covering spaces. And then we started talking about homology. So roughly speaking, we said that the nth homology group of a space was going to be the n-dimensional things without boundary divided by the boundaries of n plus one dimensional things. Right? And then we started talking about what that might mean, in particular in the case of a cell complex. Right? So we saw some things like H0 is going to be C raised to the number of path components when you have a space with finitely many path components. And we talked about how H1 is going to be like the fundamental group, but abelianized. Right? So for a cell complex, we have these groups. Cn of x is going to be the free abelian group on the n cells. Then we want to have a map that expresses the boundary of the n-dimensional cells in terms of the n-1 dimensional cells. And the homology group was then the kernel of the n mod out by the image of the n plus 1. Right, so we're going to call these cycles and these boundaries. Okay, so at the end of class, we saw that the problem or the difficulty is in defining this boundary map because you need to take orientations into account. Right? And so while that's easy when you're talking about points or paths, it's a bit complicated in general dimensions. Okay? So that's where we stopped, and now we'll make this formal. Yes?
What is H0 when there are infinitely many path components?
Yes, so we'll get to that, but not to keep you in suspense. So it's just going to be the direct sum over the path components. Right, so when you have infinitely many factors, then you have to worry about whether you're taking direct sum or direct product. Right, whereas if you have finitely many factors, it's the same thing.
Which is the one where like only finitely many?
This one.
This one.
Yeah, so the direct sum, only finitely many things show up, whereas the direct product, infinitely many can.
Okay.
Great. More questions on what we did last time? Okay. Great. So, so today we're going to see a different way of approaching this. Well, actually the same way of approaching this, but a way of making this easy to compute. And what we're going to do is we're going to restrict the type of cell complex we're looking at to ones where this is easy to compute. Right? So we're going to use cell complexes that are known as delta complexes. Okay, so here the delta is meant to remind you of a simplex. So let me remind you what that is. An n-simplex is the convex hull of n plus 1 points in some Rm. As long as generically, so as long as the n plus 1 points don't sit inside a smaller dimensional space than they have to, right? So for example, if n is 0, then a zero simplex is just a point. If n is equal to 1, then you take 2 points that don't coincide, and you take the convex hull, so you get a segment. A 2 simplex, just take 3 points that are not on the same line and take the convex hull, so you get a triangle. 3, take 4 points not on the same plane, and so the convex hull is a pyramid. And so on. There's the standard n simplex. So here we're just going to take n plus 1 points in our n plus 1. So we're just going to take the standard basis. So let's write it like this. So convex hull. So we'll denote this just delta n, convex hull of E0, E1 to En, where these are the unit basis, the canonical basis. Of Rn plus 1. All right, so alternately, you can just write this as the sum of Ti Ei, I goes from 0 to n, such that the sum of the Ti's is equal to 1, and they are all non-negative. Right, so it looks a lot like this. You just have a point. Here you would have, actually here you would have, in 2 dimensions, you'd have the 2 basis vectors, and so you'd have this segment. Here you would have R3, and you'd take the 3 basis vectors, and so then the convex hull looks like that triangle. Right, and then I can't draw it anymore. Okay, so that's what a simplex is. A face of a simplex is what you get by removing one vertex and then taking the convex hull. All right, is a subsimplex spanned by all but one of its vertices. The boundary of a simplex is the union of all of the faces and the interior, which we'll denote with a circle on top, is this minus the boundary. Right? So this will denote like that. Okay, so exactly what we're used to. Okay, so now if X is a topological space, a delta complex structure on X is a collection of maps here the n can depend on alpha. So we're going to have a bunch of maps of simplices into X, right, of varying dimensions. And we're going to demand that these satisfy the following. First of all, if you restrict to the interior, then this is injective, and every point in X is in the image of one of these restrictions. Right? So the images of the interiors cover X.
Would it be a homogeneous function?
Well, not necessarily. We're going to demand, moreover, that the image of one of these restrictions, and only one, right, so every point is in the interior of one of the images. Sorry, is in the image of the interior for exactly one. Notice that for a point, for a zero simplex, of course, there's no boundary, so it's equal to its interior. So being in the image of a zero simplex is fine. Counts as being in the image of the interior. So secondly, if f is a face, of delta n, then sigma restricted to f, sigma alpha, is one of the maps we have already. Is one of the sigma beta from delta n minus 1 to x after identifying f with delta n minus 1 by a linear map. Okay, so here's where we really have a big restriction, because we're saying that you have these maps from the simplices into X, but then when you look at one of the faces, right? Well, first of all, that's in the structure. This is one of the sigma betas that we have in our collection of maps, right? So it's one of the ones you have before, and it's one of those maps in the simplest possible way. So you're just taking that face that you have, and you're identifying it with the standard n-1 simplex by a linear map, right? So so you're not doing anything interesting when you have that face and you view it as the n-1 simplex. You're just linearly interpolating. Okay, and then we want to make sure that it interacts well with the topology. So this gets back to what you were asking. But what we demand is that a subset of X is open if and only if the inverse image of it is open in the standard simplex for all of these maps. Right? So this tells you that you can reconstruct the space X not just as a set, but as a topological space from these maps.
Wait, sorry. Sigma alpha inverse A for all alpha.
Oh, thank you. Is open.
Okay.
Yes.
I just have a question.
Yes.
So we're defining a delta complex, and you said this is a special type of cell complex?
That's right.
But, okay, I'm maybe having a hard time understanding, like, because I think of a cell complex as, like, a collection of, like, edges and, like...
Right. So remember, when we constructed a cell complex, we did this inductively by skeleton, right?
Yeah.
So we said, okay, you have a bunch of points. And then you're allowed to attach one cell, so intervals, by any topological map onto the one skeleton, the zero skeleton. Okay. Then you attach two cells, so disks, onto the one skeleton by any map you like, right? So the difference here is that we're saying, okay, you're not allowed to do any map you like. You use these maps. So of course, this the n simplex. So the triangle is equivalent to the disk, right? So these are cells in the sense of a cell complex. But what we're doing is we're going to put a bunch of restrictions on the maps that you're allowed to attach, the identifications that you use on these cells to construct the space.
So here n is telling you which type of part of the skeleton you're adding?
Yes. Yes. Although here we're not, this doesn't really matter, but we're not building it inductively. We're not saying, okay, you take the 0 cells and you take the 1 cells. That's sort of cooked in saying that whenever you restrict to a face, that's somebody that you already had.
Okay.
Right? So yeah, this is a type of cell complex, but we're just going to be much more restrictive in what sort of attaching maps we allow. Right? So there's an even more restrictive version, which is called a simplicial complex. And in the simplicial complex, you make things basically combinatorial. So you demand that every simplex, every one of these, would be completely determined by where you send the vertices. Right? So this is a little more general, which is great because we're going to see in a moment, for example, the torus you can build using two cells as a simplicial complex. We saw that before that you could make it a cell complex with a single 2 cell. If you wanted to do it as a simplicial complex, then you need a bunch. I don't remember if it's 6 or 14 or something like that, but you need a bunch because you're not allowed to have 2 with the same vertices. So you have to keep subdividing. So it's really about how much, you can think about it as how much do you have to subdivide, say, the torus in order to get the structure you want. So for a cell complex, not at all. For a simplicial complex, a little bit, sorry, for a delta complex, a little bit, and for a simplicial complex, you would need to subdivide it a lot. Right? But the only difference is how restrictive are you in what sort of attaching maps you allow. Okay? Yes?
So in the first condition, what exactly does it mean that one of these restrictions? Does it mean for a given for one of the alphas?
So what this means is that you give me a point in X, and I can find one of these maps so that without looking at the boundary, just looking at what it does to the interior, I cover that point. Right? And there's only one of these maps where when you look at what it does to the interior, it covers that point.
Okay.
Right? So yeah, you might have, the boundaries might be doing complicated things. But every point corresponds to a single one of these maps in that it is in the image of the interior for only one of these. Okay? More questions? Yes?
So like, for instance, if we wanted a delta complex structure on a simplex,
Yes.
we could just take the identity, the inclusion maps of each face, the inclusion maps of each face, and so on?
Yeah. Yeah.
Of course, identifying ones that get sort of double counted in the process.
Sure. Yeah. So we talk about, if you have a topological space, then you talk about a delta complex structure as being the collection of these maps. If you had the maps to start with, then you talk about this as the geometric realization. Right? So if you have this collection of maps and they satisfy these compatibilities, then you can reconstruct X, and you call it the geometric realization of the delta complex. Okay. So this, for example, prevents you, say, declaring that every point in X is a 0 cell. Well, unless you have like a finite set, right? But otherwise, this says that the topology on X can be reconstructed from the delta structure. So you can't just make it discrete unless it was discrete. Okay. Now, we want a little bit more structure because we want to talk about orientations. So we'll say that an oriented simplex is what you get when you have a simplex and an ordering of its vertices. So then we'll often denote it by just listing the vertices, right? And when we do that, what we have is like an identification. So this fixes an identification with the standard simplex. Right? So you give me an ordering of the vertices, and then we're identifying this by identifying each of the vertices with one of the canonical basis vectors, right, in order. So we have the standard orientation of Rn, and that's inducing the orientation here. Question?
So then the triangle, for instance, has 6 possible orientations?
Well, so as you know, orientations are form equivalence classes, and every vector space only has 2 possible orientations, right? So,
Okay.
so there are, equivalence. So, in terms of vector spaces, if you give me 2 orderings of bases, then I look at the change of basis matrix, and the determinant is either going to be +1 or -1, right? Well, it's either going to be positive or negative if you don't care about the lengths.
So the orientation here isn't like the full permutation. Is it going to be what? Like whether the permutation is even or odd?
Yeah, so
Okay.
2 are going to be equivalent if and only if the permutation between them is even. Yeah. Yeah.
That makes sense.
Yeah. So, but yeah, you will see when we start computing that that you don't really care about say where you start. You just care what order they're in up to that. Okay, so once you have an orientation, then a face inherits an orientation just by the induced order on its vertices. Right. So when you give me a face, then all you've done is remove one of the vertices, and so we know what order to put the other ones in, whatever order they were in before. So, for example, if I have a triangle, and I say that that's V0, that's V1, that's V2, then I get an orientation on the edges because I know how to go in the increasing direction, right? So this edge is going that way, this edge is going that way, and this edge is going that way.
Oh.
Mm-hmm. Okay, so we're going to want to be working with delta complexes with oriented simplices. So an addendum to 2, we just demand that the identification of F with the n-1 simplex preserves the ordering of the vertices. Okay?
Okay, I just want to make sure I understand what you're saying. An oriented simplex is a delta complex with this additional requirement?
It is, but it's much simpler because it's a simplex. So it's one of the ones I just erased. So it's the convex hull of n+1 points in generic position. Right? So it's really a generalized triangle. That's what we orient.
Okay.
Right? Then when we talk about a delta complex, we have oriented simplices, and so we're going to get boundary maps by using this orientation. But really what we're doing is we're just demanding this collection of maps come from oriented simplices, and that the identification of the face maps with one of these maps takes that orientation into account. Okay, so that's to say that everything is compatible. Right. So let's look some. Yes.
So are delta complexes by definition only defined on oriented simplices, or is it like this is a subset of general delta?
Right. So in life, this is a subset. For this course, they're all oriented.
Okay.
Yeah. Yes.
So am I right to think that the reason we want to use a simplex as opposed to something like a hypercube is because its group of symmetries gives us all of the permutations of the vertices?
It's much more practical than that. We just want to be able to define the boundary map. And when you have a simplex, the boundary map's very easy. Yeah.
Okay.
So, yeah. Okay, so let's look at some examples. So for the torus, as you know, the torus has identification space given by the rectangle with opposite sides identified, right? So if we want to view this as a delta complex structure, or if we want to put a delta complex structure on the torus, then here's one way of looking at it. So we're going to put another edge there. So we're going to call this 2-cell U, this 2-cell L, upper and lower. Here we have A and here we have B, just like before. We're going to make this C, and then of course we have a single vertex. So in terms of U, so let's say here's U and here's L. So the orientation on this is, well, both arrows are leaving this vertex, so it has to be 0. Both arrows enter this one, so that's got to be 2. And then this one has one that comes in, one that comes out, so that's got to be 1. Right? Same thing over here. This one has to be 0. This one has to be 2. This one has to be 1. Right? So here is the standard 2 simplex. And you have one map that maps this to U. Right? So we have a sigma, I don't know, called sigma U, that takes this one and maps it to U. Right? So notice in particular, all of the vertices get sent to a single point, right? Because all of these V's correspond to a single point on the torus, right? Same thing over here. We have, say, sigma L, and it takes this standard simplex with its orientation and identifies it with L. So again, all of the vertices get mapped to a single point. Notice that every point on the torus is contained in the interior of a single one of these maps, right? So these are just the maps from 2 cells, right? We also have maps from 1 cells, right? Every one of these faces has to have its own map into the torus, right? So we have one map going from here to here, one map going from here to here, one map going from here to here, and so on, right? Of course, that one is the same as the, well, we have a map going from here to there. It's really the same. So, you know, well, maybe I'll draw. So we have the one cell here that gets mapped to C. We have a 1 cell here, right, that gets mapped to B. So I don't need to put another one here, right? The restriction here says that when I take this map, sigma L, and I restrict it to a face, it has to be one of the maps in our collection, right? Well, here's the map. If this one goes from this 1 cell to B, right, it's already in our collection, so I don't need to put it in again, right? Same thing, I need to have one that maps to A, right? Because my picture's looking worse and worse, but that's the idea, right? So, so I have these 3 1 cells that get mapped to the 3 edges that you see labeled, and then I have a single 0 cell that gets mapped to the vertices. Right? So altogether here I have sigma U, sigma L that map from 2 cells. I have sigma A, sigma B, sigma C that map from 1 cells, 1 simplices, and then I have sigma V that maps from a 0 simplex. Right? And this collection, this gives me a delta complex structure on the torus. Right? So again, notice that every point in the torus is contained in the image of the interior of a single one of these. right? So if you pick any point here, well, of course, that's from the interior here. If you're on one of the edges, then you're not in the interior from sigma u or sigma L, but you are in the interior, unless you're the vertex, you are in the interior map from one of these and only one of them, right? And if you are the vertex, then you're in the interior from this guy. Okay? So that's the torus. Everybody happy with the torus?
Yeah, so the only reason we added C is so that we would have triangles.
I'm sorry, say that again?
I just want to make sure, so the only reason we added this extra
Yes.
edge is that so we can have triangles?
So that we have these maps coming from the simplices. Yeah.
So when making one of these diagrams, it's important to not create a cycle with the arrowheads.
That's right. So that would mess up the orientation. Yeah.
Which can get tricky in some cases.
Perhaps.
Can you explain why you have a cycle?
Yeah, because the when you look at a triangle, this is the no matter how you pick the orientation, the vertices are going to be labeled 0, 1, 2, right? So the arrows inherit an orientation from that ordering, right? So that means every time I look at an edge, one of the vertices is less than the other one in that order, right? So that tells me which way the edge gets oriented, right? So this is the picture. You don't have a cycle, right? So if you like, it's because the orientation on the standard triangle doesn't have a cycle. So that means that when you map it into X, it can't get a cycle, right? The maps have to be consistent with the orientations. Okay, here are a couple more examples, still on surfaces so that we can just draw representation spaces. So RP2, so here the usual identification space. So you think of this as a disk, and then you are identifying antipodal points. So each edge gets identified with the opposite edge, but with the opposite orientation. Right? Here we have two vertices, so A begins and B begins at the same vertex V, but they end at a different vertex W. So a delta complex structure. Well, we're going to do the same thing. We're going to just put in a vertex C. So again, let's call this U, let's call this L. This is going to be V, W, V, W. So let's see what orientations we're going to put on these. Right, so this vertex has both arrows pointing out, so that's got to be the 0. This one has both vertices, both edges coming in, so that's got to be 2. And this one has 1 in, 1 out, so it's got to be 1. Same thing with this one. We have 2 edges going out, so it's got to be 0. 2 edges coming in over here, so it's got to be 2. And 1 in, 1 out there, so that's 1. All right, yes?
So when you chose the orientation of C, would choosing the opposite orientation be just give us an alternate definition of the vertices and triangles below?
Yeah, as long as you can define these maps that respect orientation.
Yeah, so it doesn't particularly matter how we orient C.
That's right. Well, so we're sort of doing this backwards in the sense that really you have these guys are oriented and they have maps in, and that tells you how to orient the edges. But what we're doing is we're looking at this picture and finding a delta complex structure and then describing it afterwards, right? But yeah, you can do whatever you want in the picture as long as you end up with maps from the oriented simplices, right? So in case of the triangle, no cycles. Okay, but in this case, we're fine because each of the triangles does have a 0 vertex, a 1 vertex, and a 2 vertex. So we have a good map from the 2 simplex into it, right? So in this case, we would again have a sigma u, a sigma L from the 2 simplex, sigma A, sigma B, sigma C. And here we would have a sigma V and a sigma W. Right? But you have these guys, and every time you restrict to a face, you get one of these, right, with the induced orientation. And every time you restrict one of these to a face, you get one of these. Okay, and a final one of these pictures. Let's do the Klein bottle. So if you like, we're just doing the, let's change the orientation here. A, B, and then minus B. So we're just exhausting the possibilities of the rectangle of how are you going to pick the orientations between the opposite sides. So in this case, we again have a single vertex, right? Because wherever A starts here is the same place A starts here, and this tells us that B begins and ends at the same vertex. So B begins and ends at the same vertex over there. Yeah, and so we'll do the same thing. We will just draw in the diagonal, and then we'll note that we have an orientation consistent with how we've drawn the arrows. Note that as opposed to these, where we always had 0 and 2, 0 and 2, so that it matched 0, 1, 0, 1. Here it doesn't match, right? You have 0, 2 for this triangle, and you have 0, 1 for that triangle, and that's fine. Right? That's just telling you how to map into U and how to map into L. And so again, our delta complex structure consists of these two maps, sigma A, sigma B, sigma C, and sigma V. Okay? Yes?
Sort of a follow-up question. If we had oriented C in the opposite manner this time, we would get a cycle, so that would not be okay.
That's right. Okay. Wonderful. So we have these delta complex structures. So now we can go back to what we were talking about last time and compute the homology, just like we did for a cell complex. And the point is that we will be able to define the boundary map. Okay, so simplicial homology. So we're going to have X, a space with a delta complex structure. So we're going to define delta sub n of X to be the free abelian group with generators the open n simplices E n alpha of X, or equivalently, and perhaps more usefully, free abelian group with generators the sigma and alphas. In the delta complex structure. Okay, so every cell has a attaching map, right? So you may as well use the attaching map. Right? We know that every point is in the interior of exactly one of these guys, so there's no loss of generality there's no loss at all in just using these maps instead of the cells. Right, so an element of delta nx, which we'll call a chain, or an n-chain, is a finite formal sum k alpha sigma n alpha, in which each k alpha an integer. Right, so by the free abelian group, what we mean is that you're just taking formal sums with integer coefficients of these guys. Okay, so we want to define the boundary. So, okay, let's look at the first few cases. If you have a segment oriented between v0 and v1, then, of course, the boundary is just going to be v1 minus v0. Right, and so I'm adopting the notation of describing a simplex by describing the vertices in order. Right, so this is a 0 simplex, so I just have to tell you the vertex. Right. If we had a 2 simplex like this, then the boundary is going to be v1 v2 minus v0 v2 plus v0 v1. Right? So you just imagine going around counterclockwise. And so this edge gets a plus sign, this edge gets a plus sign, that edge gets a minus sign. Yeah. Yeah. Because in math, counterclockwise is positive. If you have the standard a standard 3 simplex, then the boundary would be like this: v2 v3 plus v0 v1 v3 minus v0 v1 v2. So this corresponds to, on each of these faces, you're putting an orientation. And how do you know which one to do? Well, this is the right-hand rule, which we teach students in calculus. Right? So, okay, so just a second, this might answer your question. So this is if you're looking at things geometrically, but you don't have to look at things geometrically. There's a very simple formula. So if you have an n cycle, n simplex, then the formula is just, in terms of the face maps, this notation vi is omitted. Right, so there's a very simple algebraic way of doing this. You just remove one vertex at a time, right, which is how you get the faces, and you put a sign, alternating sign, as you do this. right? And so that's the face map. This is just the motivation from geometry for why this is a good way to define the boundary. Does that answer your question?
Yes. I do have another question.
Go for it.
Which is what happens if we have a situation like for the torus,
Uh-huh.
where we have an edge, but the starting and ending vertex of that edge are actually at the same point.
Right, you see that's fine, because we're doing this for sigma, right, the attaching map. And this is the restriction of its domain. And in its domain, the vertices are different, right? So it's fine that the image ended up being the same point in X, because you're doing this in the domain.
Okay.
Okay, very good. More questions? Okay, excellent. So because we're working with these simplices, we have this very simple way of defining the boundary map, and it takes into account orientations, right? So it fixes the difficulty that we mentioned last time for a general cell complex of how do you take the boundary. Well, since you're working always with simplices, you know how to take the boundary. Okay? So notice that if you take the boundary, of a boundary, you get 0. Right? So succinctly, we just say boundary squared is 0. Or we might put a dot to indicate whatever index. So one way to think about this is that, of course, as we mentioned, you're really doing things to the domain of the attaching map, not to the space X. So the fact that this squares to 0 is a statement about the domain, not about X, right? So it's really a statement about simplices, right? It says that if you look at the n simplex, and the boundary of its boundary is 0, right? So the n simplex looks like a ball, n-dimensional ball. So its boundary is the n-1 dimensional sphere. And so this is really just the fact that a sphere has no boundary. Right? So this is this corresponds that the sphere has no boundary. Okay, but that's neither here nor there because it's a purely algebraic or combinatorial fact, right? So if you have sigma, we know what, I don't need to write it again because it's right there. So dn minus 1 composed with dn of sigma is going to be the sum of minus 1 to the I of, okay, so I'm going to take the boundary of the boundary. I should say here that, of course, this is how you define the boundary on each attaching map. I want the boundary to be defined on the free abelian group with these guys as generators. So you just extend it linearly. Right? So, okay, great. So if I take the boundary of the boundary, I'm going to just be taking the boundary of this sigmas restricted to faces. Right? So that means I'm going to take an alternating sum where I remove a vertex, right? From here where I've already removed one vertex. So I'm going to have a sum minus 1 to the j of sigma alpha restricted to, and well, the thing is that the sign is going to be a little different whether you remove vj before you remove vi or after. So it's going to be minus 1 to the j if j is less than I, but it's going to be minus 1 to the j plus 1, or minus 1 if you prefer, sigma alpha restricted to here where the vi comes before the vj. Okay. So now the thing to note is that each of these face map of a face map occurs here and here. Right? So if here, let's say I removed the third vertex and the fifth vertex, then of course here, Vi being 3 and Vj being the fifth vertex means that the same face map showed up. Right? So I have really the same face maps showing up, and one time they show up with sign -1 to the I, -1 to the j, and the other time they show up with sign -1 to the I, -1 to the j -1. So each one of them shows up exactly twice with opposite signs. So you get 0.
It's slightly tricky because the 2 times they show up, you're switching I with j.
That's right, but you know, they're just dummy variables. Yeah. Yeah. So you could think just which is the smaller vertex that you removed and the next smallest vertex you removed, and not worry about who's I, who's j. Okay. Great. So we like it when this happens so much that we give it a name. Right? So a chain complex let's just see, and it doesn't have to. A chain complex is a sequence of abelian groups and group homomorphisms such that they square to 0. Notice that if this is equal to 0, that tells you that the image of delta n, do I have this the right way around? Yeah. Is inside the kernel of delta n minus 1, right? Or, yeah, that's fine. So we define the homology of the complex to be the kernel of dn mod out by the image of dn plus 1. Right? So the kernel's an abelian group, so every subgroup is normal, so it makes sense to take the quotient group, and I always get an abelian group. Right? So this is the homology of the complex. These are called cycles. These are called boundaries. The elements of here are called chains, hence the chain complex. Okay, so this is a situation we like a lot. So we give it everything its own name. And what we've shown over here is that whenever you have a delta complex, you get a chain complex. All right, so we've shown that you can take whenever X has a delta complex structure, then this gives us a chain complex. Yes?
Sorry, is that H out of C naught or C dot?
C dot.
Okay.
Yeah.
Thank you.
Sure. So yeah, we use dot a lot when we just want to have a place where the indices run. Yes?
So when we're using these boundary maps to go now from these free abelian groups, presumably what we're doing is we're using the boundary map on each of the generators and getting a natural homomorphism that way?
That's right. So you extend it linearly to the free abelian thing. Yeah. That's right. So whenever we have a delta complex structure, then we have these groups, these maps, and so we define Hn delta of x to be the homology of this chain complex. Right? And we call this the simplicial so this is the nth simplicial homology group of X. So you could wonder, why do we call it the nth simplicial homology group of X if we used a delta complex structure on X to define it, right? And so, of course, implicit in that is a claim that it's not going to depend on what delta complex structure you put, only on X, right? So we'll now work our way towards that.
So earlier we just defined the nth homology group of X?
Well, we suggested what the nth homology group of X was because we didn't have boundary maps, and so we didn't quite define it.
Okay.
Right? But for a cell complex, we did define, say, H0, H1, talked about H2.
So will that turn out to be equivalent to this then?
Yes.
Okay.
Yes. So it turns out, just to jump way ahead, it turns out that there are many different ways of defining homology of a space. And then there's a beautiful fact, a wonderful fact, that as long as the homology theory satisfies like 5 obvious axioms, then it gives you the exact same groups for every cell complex, right? If you have a crazy space, then anything can happen. But if you're only working with cell complexes, then all of these different theories give you the same groups. Right? So that is really useful. So in particular, this is, for cell complexes, you get the same groups always. Right.
So it's kind of like what homology groups are is just it's sort of similar to like Euclidean geometry. You just have like 5 axioms and then all the structure follows from those. And then what we've just defined is sort of the equivalent of just, Euclidean space, like here are some coordinates, here's what distance means.
Yeah, so anytime you have an axiomatic system, then you can give examples of things that satisfy those axioms, right? So yeah, I will give you soon a list of axioms, and
Assuming the axioms are consistent.
that's right. Okay. So let's do a couple of easy examples. So let's do S1. So put a delta complex structure with 1 vertex and 1 edge. Right? So let's pick a vertex and then there's your edge. So, okay, this one is really easy, right? Because the only groups that are going to show up are delta 1 and delta 0. Right? This is the free abelian group on our single edge, and this is the free abelian group on our single vertex. The boundary of edge is 0, right? Because it begins and ends at the same vertex. Yes?
So that's circle, that's a copy of S1 on the left, but 0 on the right, yes?
On the left. The chain, so this is
The first thing you change before
this is 0.
that's also 0.
Yeah, that's right. It's not a circle. Well, it is, but it's not representing the circle, right? It's 0. The abelian group 0. Yeah. Yes. Whereas this is the abelian group Z, and this is the abelian group Z. Right. Just a copy of the integers, right? With generator the edge, and this one with generator the vertex. Right. So the boundary, okay, well, the boundary is going to be, I've erased, but it's going to be the ending vertex minus the beginning vertex, right? But there's only one vertex, right? So the boundary map is just 0. Okay, so, okay, all of the boundary maps are 0. So Hn of, well, the circle is equal to the kernel of boundary n divided by the image of boundary n plus 1. But if all of the boundary maps are 0, then the image is always 0, and the kernel is always the whole group. So we get z if n is equal to 1 or 0, well, let's put 0 or 1, and 0 else. Right, so those are the homology groups of S1, which are not surprising because we already know that the 0th homology group is just going to count the number of path components, and the first homology group is going to be the abelianization of the fundamental group. Right, so which is already abelian in this case, yeah. So the only thing that's new compared to what we knew before is that you don't get anything above that. So homology is not going to take a one-dimensional thing and find some two-dimensional hole in it, right? It stops. Let's do the torus. Right, so the same delta complex that we had before, delta complex structure, with delta complex structure. Oh, here I should have labeled this with delta, because we're computing it for the delta complex structure. Okay, so we saw this one is going to have a sigma u, a sigma l, sigma a, sigma b, sigma c, and sigma v. Right, just like we had before. Let's draw A, B, C. This was U, this was L. Right? So, okay. So we only have things in delta 2, delta 1, delta 0. Right? This is the free abelian group on U and L. This is the free abelian group on ABC. And this is the free abelian group on V. Right? So this looks like C2, this looks like C3, this looks like C. Okay? And now we want to look at what are the boundary maps. So the boundary of U Okay, well, boundary of U is going to be, right, look at a, going counterclockwise, you're going to get C minus A minus B. A plus B minus C. 0, 1, 2. 0, 1, 2. 0, you get 1, 2. A. No, got the sign wrong. A plus B minus C. So let's do it carefully. So we know that U, sigma U, has vertex 0 here, 1 here, 2 here. Right? So the boundary of sigma U is equal to sigma U restricted to V1, V2 minus sigma U restricted to V0, V2 plus sigma U restricted to V0, V1. Right? That's the definition of the boundary map. So if you're going from V1, V2, so V1, V2, that's A. Right? So this is sigma A. This guy from V0 to V2 is sigma C, and here V0, V1 is sigma B.
So it wasn't counterclockwise?
Well, it's counterclockwise from a different, right? So if you were to put this so that it looked like the standard one, then it would be counterclockwise, right? But the 1 is in the wrong place for that, so it looks clockwise. Right? That's right. So it's counterclockwise if you look at it from the other side. Yeah. But anyway, so it's with respect to the standards of, yeah. Also known as clockwise. Yeah. Yeah. But so if you do it carefully, then you don't have to worry about the picture, because the algebra will tell you. So we get, indeed, A minus C plus B, like that. Okay? So on the other hand, for L, we had 0, 2, and 1. So this one is set up the right way. So we can just look at it, go counterclockwise. Right? Okay, so that one, so boundary 2 of L is going to be A plus B minus C. Okay, so the boundary 2 is the same for U and for L. So that makes it easy to compute the kernel. So it's going to be all of the K times U plus L times, bad choice, J times U plus K times L, such that J plus K is equal to 0. Right, because they have the same boundary. Okay, so H2 of the torus, this is the kernel of D2 mod out by the image of D3, but there are no 3 cells, so this image is 0. So it's just a kernel of D2, right? And that's a copy of Z. Right? And anyway, if you like, it's KU plus JU plus KL such that J plus K is equal to 0. Right? But that's just said. H1 of pi 2 is equal to the kernel of D1 divided by the image of D2. Okay, now all of the edges begin and end at the same vertex. So they all have no boundary. Right? So the top is just a free abelian group on ABC. The image of the boundary is the free abelian group with a single generator, a plus b minus c. Right? So that quotient is really easy, right? Because c becomes a plus b. So you just have the free abelian group on AB, say. Right? C squared. And then H0 kernel of D0 over the image of D1. Well, this is 0, and so this is equal to the free abelian group on our single vertex, so we get Z. Okay. Okay, let's do one more. So let's do RP2 with the delta complex structure above. Right, so how do we draw it? We said this was A, so it has to be opposite over here, and then this was B, opposite over here. And we do C, and here we have two vertices, V, and W and W. Okay, so we call this U, we call this L. And let's draw the triangles from the beginning this time, so we don't get it wrong start. 0, 2, 1, 0, 2, 1. Right. So this one, they're in the correct order, so we could just go counterclockwise. This one, they're in the wrong order, so we'd have to go clockwise. So boundary 2 of U is going to be C plus A minus B. Boundary 2 of L is going to be C plus B minus A. Boundary 1 of A is going to be W minus V. That's also boundary 1 of B, whereas boundary 1 of C is 0. Right, because C begins and ends at the same edge, same vertex. Okay, so we start out with our chain complex. It only has delta 2, RP2, delta 1, delta 0. Right, this is the free abelian group on UL. Free abelian on ABC, free abelian on VW. Okay, H2 delta is going to be the kernel of delta 2 over the image delta 3, so that's just the kernel of delta 2. Okay, so what is the kernel of delta 2? Well, if you have delta 2 of, say, j times u plus k times l, that's going to be j times c plus a minus b plus k times C plus B minus A. So that's J minus K times A plus K minus J times B plus J plus K times C. Right? So if this is equal to 0, then J has to be the same as K, and J plus K has to be 0. Right? So this is equal to 0 if and only if J is equal to K is equal to 0.
So the kernel is trivial?
So the kernel is trivial. Right? So this is 0. Okay, let's take a look at the image of delta 2 is going to be, so it's, well, let's just write it out. It's going to be J times C plus A minus B plus K times C plus B minus A, right, which we could write as, take any multiple of A minus, let's say for abelian, A minus B and 2 times, or just 1 times C. I want 2 times C. If I add them to C. Right, because if I do, let's do this. Yeah, if you want to get rid of the A's and B's, then you need J to be equal to K, right? So you get a multiple of 2C, right? So these linear combinations give you the free abelian group on A minus B and 2C. So H1 delta of RP2 is free abelian group on A, B, C, and then you mod out by the free abelian group. Let's see what I want. That's what I'm doing wrong. This is not A, B, C. It's A minus B, comma C, because we saw over here that delta 1 of A and delta 1 of B, they're not 0. They're just the same. Right? So you get the free abelian group on A minus B, comma C, and you mod out by the free abelian group on A minus B, comma 2C. So A minus B just dies, and you end up with C mod out by 2C. Right? So that's C mod 2C. Right? And then H0 delta of RP2 is the free abelian group on VW mod out by the image, which is the free abelian group on V minus W. So you end up with just C. Okay, and that's where we'll stop.
And again, we get H0 is just Z to the power of the number of path components, which is 1.
Exactly right.
And H1 is the abelianization of the fundamental group,
Exactly
which
right.
was already abelian and was Z over 2Z.
That's right. Perfect. So next time we'll show that it doesn't depend on the choice of delta complex structure.